All right, good afternoon, morning, night, or whenever it is you're watching this. So, we are going to basically continue on with where we left off, before the break happens. So, where we left off, we were looking at, or I had you guys do the isomers for our all isomers of C7H16. So if you want to look up all these here, of course, hop online. I'll have hop on Google Classroom or my website where the links to the answer key will be posted. All right. So for today, we're actually going to be looking at cycloalkanes. Now, of course, with these here, we see the word cyclo in there. That means that we have a closed ring, or what we call in organic chemistry, a cyclic structure. Now, so the general formula for this is CnH2n. So if we have something like cyclopentane, where we know pent is equal to 5 carbons, that means if we want to figure out the general formula for cyclopentane, we can go C5H2 times 5, or C5H10. Now, how this will look, of course, for this cyclic or this closed ring structure, basically that means that we have the ends of our normal pentane molecule connected to make a closed ring. So how this will look, I'm just going to do structural formula here now. So we have one carbon, another carbon. So we're going to get 5 carbons bonded together like this in a closed ring. All right. Now I know this isn't the prettiest looking thing that I've ever drawn, but that's fine. Now, when we got to figure out, of course, how many hydrogens there are, so I have 5 carbons in a closed ring, so we need to have 10 hydrogens around total. Now, if we look at every single carbon that's bonded here, we can tell that even this carbon right here, right, we have 1, 2 bonds already into it, so it could only take a maximum of 2 hydrogens to complete the 4 bonds that carbon needs. And every single carbon can take 2 hydrogens. So that's why the formula exists. Now, drawing these here in structural diagram is not a lot of fun. So normally we use line structures for our cyclic compounds, which it would look something like this, kind of like a pentagram, or in this case here, it looks like a house. But either way, we can tell that we have 5 carbons enclosed in this cyclic structure. So as we are naming these here, we are going to place the prefix cyclo in front of the alkane name. So this is going to tell us that, of course, it is in a closed ring. Now, take a special note here. So if there's only one branch, no numbering is required. That is because if you have like methyl cyclohexane, you just draw a methyl off that closed ring structure. It's assumed that carbon 1 is always closest to the first branch, and because we have this closed ring structure, carbon 1 is going to be on a branch. Now, if there are 2 or more branches present, we have to number so that we get the lowest possible combination. So what that means is that we try to get as many branches on carbon 1 as possible. And then, of course, we try to get as many branches off carbon 2 as possible. So it's going to be like that. So lowest possible combinations. Now, if 2 different branches are located on the 1 and 2 position, we list them alphabetically, just like we did with our alkanes. Now, and this could be number 1 and 2. Lost train of thought there. So if we do have this possible, or 1 and 2 or 1 and 3 of cyclic structure, carbon 1 is going to be the one listed alphabetically. And we'll kind of get into that now in a bit. So we usually represent this line diagram. So let's have a look at our first few examples and start naming them. So our first step is that when we look at a cyclic structure like the one we have right here, we're first going to count how many carbons there are. Now, I'm also going to count the carbons and place carbon 1 where I'm going to get the lowest possible combination. All right. So in this case, we only have 1 branch, this one right here. So carbon 1 is going to be right on the branch. So this way, we're satisfying that rule that carbon 1 is closest to our first branch for naming alkanes. So now it doesn't matter which way I actually name it because there's only 1 branch, so we'll get the same name however we list it, but I just want to count how many carbons we have. And in total we have 8. So because we have parent equals octane, I'm going to write cyclooctane because it is a closed ring. I'm going to try to write it. Cyclooctane. And yes, there are two O's together. Now, as for our branch, this is the only one that we have right here. It is one carbon. One carbon is meth. And to signify it is a branch, we end it with YL. Now, as we are naming it, it says right here in that special note that if one branch, no numbering is required. So we have one branch. So this is why we're going to have methyl cyclooctane. So you will notice we are keeping with the IUPAC naming system where our branch is listed first and our parent chain is listed last, right? But the only difference right here is that we have this cyclo indicating that it is a closed ring, and specifically we have 8 carbons that are all have single bonds. Now for our second one, we can tell that there are 2 branches. So because of this, I am going to have to label them. All right. Now for carbon 1, I am going to put on a branch, and then I'm going to try to get the lowest possible numbers. So if I create carbon 1 right here to get my lowest possible numbers, carbon 2 needs to go there. And then I label all my carbons going around and find out that my parent chain, just like the last time, is equal to cyclooctane. And now for my branches, we can tell we have this one right here, which is 1 carbon, and this one right here, this is 1 carbon, so these are methyl. Now to name it, because we have more than one branch, we actually need to include the position and the names of our branches. So we can tell we have methyls off carbon 1 and 2, so I'm going to start by writing 1, 2, dash. So remember, dashes separate our numbers and letters. Now because we have 2 methyls, we write di for 2, and then we write methyl. So these are all the branches taken care of. We have our 1,2-dimethyl. Now we have to write our parent chain, which is cyclooctane. And that is the name of this particular organic molecule. Now, we are going to increase the difficulty here by increasing the total number of branches. And that's going to be in our next few examples. So if you want to try these on your own before I go over them, please pause the video, try it, and then see if you get the right answer. If you're going to continue listening, then all right, here we go. So with our next one right here, we can tell that we have a bunch of different branches. Now we are going to make use of the rule that we are going to try to get the branches off the lowest numbers possible. So if we can get a branch off of carbon 1, well, carbon 1 is the lowest possible number. But if we can get branches off carbon 1 twice, 1, 1, that combination of 1, 1 is definitely the lowest possible number combination. So because of that, I need to stick carbon 1, I have to stick carbon 1 right here. This way I have 2 branches off carbon 1, which is the lowest possible combination of numbers. Now in order to get the rest of the branches off lowest possible combination of numbers, I need to do number 2 here, 3 here, 4 here, 5 here, and 6. So our parent is going to equal cyclo, in this case here, 6 carbon, so it's hexane. And as for my branches, now this is 1 carbon, so these are both methyl, and this is methyl. This one right here, we notice that we have 1, 2 carbons connected in a row, so this is ethyl, and then down here we have methyl. So just notice the difference how we have our 2 methyls up here at carbon 1 and how that looks, or the difference between a dot or 2 methyls up here and then an ethyl, right? An ethyl is 2 carbons connected one after the other. These are just 2 methyl groups off the same carbon. So now when we actually name this right here, because we have different branch names, now we need to consider the alphabet when numbering or naming it, sorry. So E comes before M in the alphabet, so we're going to have to name our ethyl first. And we have our ethyl off carbon 2. So this name is going to start with 2-ethyl. So that is that branch. Now we need to name our methyls. So we go dash. Sorry for that popping up. We have methyl groups off carbon 1 and 3. Specifically, we got 2 on carbon 1. So we go 1, comma 1, then comma 3. Now there are 3 of them. So that's trimethyl. So that is all of our branches. Now we need to name our parent chain. So our parent chain we already have listed up above is cyclohexane. All one word. So we got 2-ethyl 1,1,3 trimethyl cyclohexane. And that is that name. Now I would like for you to pause the video and try the last one on your own. Okay, so hopefully you pause it and try it on your own. So the name for this one right here, we have carbon 1 needs to start here for the same reasons. We can get 2 branches off carbon 1, and then to get the rest on lowest numbers possible, we got 2, 3, 4, and 5. So the name for this one here, when we get going, we got a 4-ethyl 1,1,2 trimethyl cyclopentane. I'm sorry I couldn't fit that all in the one word, but hopefully you guys get it going across here. So 4-ethyl 1,1,2 trimethyl cyclopentane. All right, so that is the naming of our cyclic alkanes. Now the drawing. All right, so the drawing for these here, I kind of like the drawing more than the naming because we get to break down the name and then of course draw and put carbon 1, carbon 2, carbon 3 where we want to as long as they're in consecutive order. Now when you're drawing, your first step is always look at the end, right? Because this is our parent chain, it's the first one that we should have. So we see the word cyclo, so we know it's going to be a closed structure, and we see propane. So propane we know is 3 carbons, right? So prop is 3. So therefore, we need to draw 3 carbons in a closed ring. So that means I'm going to do line formula. So we got 1, 2, 3. That is what cyclopropane is going to look like. It's just a triangle. That's how we get 3 carbons in a closed ring. Now for this right here, we can stick carbon 1, carbon 2, carbon 3 wherever we want. So if I want to go carbon 1 is here, then 2 here, and 3 here, that means off carbon 1 I have a methyl, and carbon 2, oops, sorry, that didn't come out very well. We have carbon 2 right here for my other methyl. So that is my 1,2 dimethyl cyclopropane. Now, of course, this works for all of them as long as you follow those steps. All right. So the next one, same thing. We're going to look at the ending first to figure out what the parent is. And our parent is cyclohexane. So this is where those geometry skills and math that you've done long ago is going to pay off. So hex is 6 carbons, so we are going to create basically a hexagram. So it's going to look like this. I know it's not the prettiest looking thing, but we can tell we have 1, and actually, no, let's name them or number them. So we got 1, 2, 3, 4, 5, and 6 carbons. Just like that. Now, off carbon 1, we see 1,1,22 tetramethyl, right? So 1,1,2,2 tetramethyl. So that means off carbon 1 we get 2 methyl groups. So we go 1 and 2, like that. On carbon 2, we also have 2 more methyls. And there is our 1,1,2,2 tetramethyl cyclohexane. Now, I would recommend pausing the video right now, drawing in the other 2, and then unpausing it to see what they are. And then, of course, I'll just give you a second to pause. And welcome back. So here is our second last one. So 3-butyl 1,1,2 trimethyl cyclopentane. So our cyclopentane, 5 carbons in a closed ring. It doesn't matter where you stick carbon 1. I'm going to stick carbon 1 right here, then 2, then 3, then 4, then 5. So we have 1,1,2 trimethyl, so 1,1,2 trimethyl, and 3-butyl, 1, 2, 3, 4 carbons. So that will be our 3-butyl 1,1,2 trimethyl cyclopentane. And the last one, we got 1-butyl-2,4-dimethylcyclohexane. So we draw our cyclohexane. So we got 6 carbons in a closed ring. I'm going to label carbon 1 right there. You can do it whichever way you want, but I just choose that one. So off carbon 1, I'm going to have my butyl, which is 4 carbons. So I go 1, 2, 3, 4. Off carbon 2, I have a methyl, and carbon 4, I also have a methyl. And that's what our 1-butyl-2,4-dimethylcyclohexane will look like. So that is it for this particular lesson on cycloalkanes. Now it would be an excellent time to go to your workbooks and start working through the naming of the alkane sections. And when you are done that, please come back and we are going to go over how to name our alkenes, alkynes, cycloalkanes, and cycloalkynes. All right, see you guys later.